Yeah, whatever. Okay, so most important thing in all of physical science is that opposites do what? Attract. And likes do what? Repel. What in the atom is opposite?
Protons and electrons.
Protons and electrons. So protons are positive, electrons are negative. They attract. What in the atom are the same and repel? Neutrons are neutrally charged. Protons are positive, electrons are negative, they attract. What are the same and repel? Electrons and electrons, exactly. Electrons and electrons repel each other. Now, when we talk about nuclear, we learned that protons and protons also repel each other, but the neutrons hold them together. Well, we're going to learn a kind of an interesting concept today that fundamentally affects everything else in chemistry. And that is the electrons, see the electrons, the electron cloud, are attracted to the nucleus. But electrons are in shells. And the inner shell repels the outer shell. Well, I'll diagram it for you. It's a great little cartoon that AI made for me after a few attempts. Google, hello. There we go. Okay. So this is how it works. In the nucleus, we have a bunch of protons chilling out. I'm going to make this a neutral. So there's 5 protons, and if it's neutral, how many electrons should there be? 5. 5 positives, 5 negatives. If it's going to be neutral. So then we have a bunch of shells. There's a shell, and there's a shell, and we don't need any more shells. How many electrons are going to be in the first shell? How many electrons are in this shell? 2. There's 2 electrons in this shell. There's 1, there's 2. This is the 1s1. This is the 1s2. Looking familiar?
Yes.
Okay, so how many electrons are left?
3.
3. And they're going to be here. This is going to be the 2s1. This is going to be the 2s2. And what's the third one? 2p1. 2p1. Okay? So that's a total of 5 electrons. It's a neutral atom. So if we're going to have 5 protons, we're going to have 5 electrons. So far, so good? Okay. So these 2 inner electrons, what do they do to the nucleus? What are they doing towards the nucleus? Exactly, they're pulling in. So these guys are attracted to the nucleus. Make sense? Are the outer electrons attracted to the nucleus?
Yes.
They're still electrons. They're also attracted to the nucleus. But there's an issue. Their attraction is somewhat rebuffed, canceled out, by the repulsion of these 2 electrons for that electron. So this is repel. This is repel. So the inner electrons are pushing out against the outer electrons. If that wasn't there, all the shells would just collapse on themselves. And there'd be one massively dense shell. So the inner shells keep the outer shells further away, so there's a balance. If you looked at the attraction of this shell for the nucleus, it would go up with distance, or it would go down with distance. But if you look at attraction for this guy for the nucleus, which one's going to be stronger? Which one's going to have a stronger attraction? Shell 1 for the nucleus or shell 2 for the nucleus? Shell 1, it's closer, right? If you want to do the math, the math is over there somewhere in the physics part, which is mathy stuff. So this shell's attracted, this shell's attracted, but its attraction is mitigated, that means reduced, by the inner shell. This is super important because this is what every other property we're going to learn today hinges upon. So we say the attraction is based on the effective nuclear charge. Effective nuclear charge works like this. It's the number of protons that each electron sees effectively. It's the number of protons that each electron is attracted to effectively. So this electron and this electron, how many protons are they attracted to? This one's attracted to how many protons?
1.
Oh, 5. This one's attracted to 5 protons. How many electrons is this one attracted to? 5. This one's attracted to 5 protons. But then the outer shell is interesting. The outer shell is attracted to 5, but blocked by 2. So this outer shell has an effective nuclear charge of 3. Same with this one. Same with this one. The outer shells, they're attracted to 5 protons, but they are repelled by 2 electrons. So we say they have an effective nuclear charge of 3. Does that make sense? Because this is super important. Everything else is based upon this idea that the protons pull in the electrons, but the inner shell electrons push out against the outer shell electrons. And it is that balance of attraction and repulsion that causes all the properties that we're going to be learning today. Okay? If you're with me so far, give me a thumbs up. If any part of this is in any way unclear, wave your hand around. Okay, so how this works is pretty simple. The effective nuclear charge can be basically summed up with the number of valence electrons. Remember valence electrons? Group 1 has 1 outer electron. Group 2 has 2 outer electrons. Group 3 has how many? Sorry, group 13. Group 13 has how many? The valence electrons are from the highest s and p orbitals. So if you look at like lithium, number 3, lithium has 2s1. How many valence electrons? 1, exactly. Beryllium is 2s2. How many valence electrons? 2. Boron is 2s2, 2p1. How many valence electrons? 3. Carbon is 2s2, 2p2. How many valence electrons? 4. See how that goes? So it's 2 plus whatever the p is. You get down all the way to neon, it's 2 and 6, so that's 8. Oxygen, 2 and 4, that's 6. So far, so good? So all you do is you say, all right, let's see, where's the, did I put the little math for you or just kind of give it, yeah, okay. We're not going to worry about the math, we're just going to worry about the concepts. There we go. There's a little formula, but we don't have to worry about that. So all you do is you say, all right, how many valence electrons are being attracted to the nucleus? How many of the inner shell are pushing out against those valence electrons? So when you look at this, and by the way, the math, again, the reason I got rid of the formula is the math is like really approximate. The trends are way better, just to realize the overall trend. So here's helium. It's got 1 proton and no shielding. That's like pushing back. The shielding effect is pushing back. So it's got 1 proton, no shielding, so it sees an effective nuclear charge of 1. Helium has 2 protons, 2 electrons, effective nuclear charge of 2. Then you get to lithium. Lithium sees 3 protons, but there's 2 electrons in the inner shell. So lithium's effective nuclear charge is only 1. Is that clear? It's just the number of protons that the atom would see, which is based on remember the atomic number is the number of protons. It's the number of protons the atom would see minus how many electrons are in the previous shells. So beryllium, 4 minus 2. 4 valence electrons minus 2. Boron, 5 electrons minus 2. Carbon, 6 electrons minus 2. 2 because there's 2 in the inner shell. Nitrogen, 7 minus 2. Oxygen, 8 minus 2. Fluorine, 9 minus 2. Neon, 10 minus 2. And then we get to sodium. Sodium is in shell number 3. It is blocked, repelled, or shielded by shells 1 and 2. Is that clear? Sodium sees, it's atomic number 11. How many protons does sodium see? Overall. It's atomic number 11, which means there's how many protons? 11. Sodium sees 11 protons, but is shielded by the previous noble gas is neon. How many electrons does neon have? 10. Sodium sees 11 protons, but is shielded by 10 electrons. So sodium has an effective nuclear charge, once again, of 1. Now, the reason it's not exactly 1 is for reasons, I'm not going to get into them. But you can realize it's basically, when you look at the effective nuclear charge, it's basically how many protons the electrons are attracted to minus how many how many electrons are in the previous shells. 11 in, 10 back, effective nuclear charge of 1. Okay. If this is clear to you, give me a thumbs up. If any part of this is unclear, wave your hand around. Okay, so that leads to, do you like my animations I had the AI make? AI is great. I probably killed 100 fish doing this. Heat up those rivers, kill those fish. Now, it's super important when you take the test, which is the end of next week. About half the questions will be what's. What happens here? Which atom is higher? Which atom is lower? About half the questions are going to be why. So half of them are going to be, of this atom and this atom, which atom is larger? And about half the questions is, this atom is larger than this one, explain to me why. Yes?
How did you kill 100 fish making that atom?
Because AI, good question. So AI works on computers. Computers have to be kept cool. So they basically run massive channels of water through the data centers to keep them cool. And that warms up the water. Here's the problem. When you imagine you have two liters of water, 2 liters of soda. One that was in the fridge and one's been on the countertop for a while. You open them up, which one makes the bigger fizz? The warm one. Which one goes flatter first? The warm one. Because warm water allows less gas to dissolve in it. Cold water allows more gas to dissolve in it. I'm gonna say this again in April. So if you warm up the water, less oxygen can dissolve into the water. You realize fish need oxygen to breathe, right? Just like our lungs pull the oxygen out of the air, their gills pull the oxygen out of the water. If there's not as much oxygen in the water, the fish don't live as well or as long. So you warm up the waters, you kill the fish. It's that simple. Did that answer your question?
Yeah.
Other questions? Yeah. AI is just... Yeah, it got you that. So you better use that in a way to make the world better because, geez. Okay, moving on. Our first trend is just how big an atom is. And it's pretty important. So we use the word atomic radii to mean the distance from the center of the nucleus there to where the outer shell of electrons is. And as you might notice, as you go across the periodic table, it gets smaller and smaller and smaller and smaller and smaller. Why does it get smaller, 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 smaller as you go across the periodic table?
The more protons and electrons there are, the stronger the magnetic field.
Exactly right, except for not magnetic electric.
Well, electron.
Yeah, so the analogy we use was multiple magnets, like 4 magnets versus 2 magnets. 4 magnets are going to be pulled together stronger than 2 magnets, but it is a similar force. It's not electric force. Sorry, it's not magnetic force, it's electric force. Literally called electrostatic attraction. Yeah, so more protons, more electrons are going to squish the electron cloud. So as we go across the period, we're in the same shell, the same group, the same shell, the same energy level. They're going to get smaller, 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 smaller as we fill up that level. But as we add protons, there's more protons attracting more electrons, and the atom shrinks because of the electrostatic attraction. And as we go down the periodic table, we add new shells. And the new shell, listen carefully, all the electrons in the new shell have a very low effective nuclear charge because they're shielded from all the previous shells. So that first shell goes, yay, protons! And they're like, whoa, there's a lot of electrons in there pushing me back. And that's why when you start a new shell, the atom is huge. Imagine an outside electron zooming around that green dot. So as you add a new shell, those inner shells shield the electrons in the new shell, and that new shell gets pushed way out. Okay. Questions? Yes?
I'm like a little confused.
Cool. Okay. Well, then let's talk about it again. Thank you for being honest. In the same shell, energy shell, as we add new protons in the nucleus and new electrons in the shell, the protons are attracted to that shell. And since there's more protons attracting more electrons, they get pulled in. It's kind of like if you tried to pull away 2 strong magnets versus 8 strong magnets. It's going to be harder to pull away 4 and 4, and then it's going to be 2 and 2. Make sense? Okay. So as we add new electrons and new protons, the attraction, the nuclear attraction for those electrons is increased. Squish, 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 squish. But then as we go down a level, we're adding an entirely new shell of electrons, so that outer shell gets repelled by the inner shell. Cool? Other questions? Okay. I'm recording this. The correct answer to why does the atomic radius get smaller from left to right, or more accurately, the correct answer to why is calcium smaller than potassium will not be because this property gets smaller from left to right. And the correct answer to why is potassium larger than sodium will not be because this trend gets larger top to bottom. You're always going to talk about electrons, protons, attraction, and repulsion. That's always going to be your explanation in the essay questions. GTTP will back me up on that. All right, next. The next property is ionization energy, and it is how much energy you and I have to apply to pull an electron off. We have to create an electric field that will extract an electron from an atom. Ionization energy is how much energy it takes you and me to pop that electron off. Now, if you only have one electron in an outer shell that has a very low effective nuclear charge, like the alkali metals that have one outer electron, and that outer electron is pretty well shielded from the nucleus, is it going to be relatively easy to remove an electron or relatively hard? You're like hovering over the atom, and the atom's right there, and you're like, I want to remove the electron. So I'm going to create an electric field, I'm going to crank up the juice until that electron pops off. Is it going to be easy to remove a single electron that's very shielded? Mm-hmm.
Yes.
It is. It's very easy because that outer electron, it's the only one in the shell, and it's heavily shielded. On the other end of the periodic table, especially with the noble gases, they have a lot more protons, but the same amount of shielding. So if you compare sodium, which is shielded by 10 electrons, to argon, which is shielded by 10 electrons, argon's got a lot more protons, but the same amount of shielding. So it's extremely hard to remove an electron from elements over here. As you have more protons, but the same amount of shielding, it becomes harder to remove an electron. Because there's more protons.
How come when you go down a slide you get shocked?
It's friction. Okay, so this is fun. I love having Evan in class. Thanks, Evan. This is a great question. Some materials have a very strong attraction for electrons. Some materials have a very loose attraction for electrons. So things like rubber have to, they love getting, there's lots of places for the electrons to be in the material. So they take electrons very, very easily. And things like fibers, like cotton and polyester, they have a lot of electrons that are very, very available. So as you slide down, the fibers in your clothes are shedding electrons to the slide. That makes you positively charged and makes the slide negatively charged. So then when you touch something, those charges will tend to zoom back together. Same thing when you get out of your car. So this used to be a big deal. So they would say, do not go back into your car when you're pumping gas. Because what would happen is you'd get out of the car and you'd touch the pump and you'd ground all your extra charges. Because the process of getting out of your car, your clothes rub on the nylon or the vinyl seat, and that charges you up. And then you touch the pump and your charge dissipates into the pump. But then you go back into your car and you sit there for a while until it goes click, click, then you get up, same way, now you're charged, and when you try to touch the pump, a little static lightning will click and light the vapors on fire. And there'd be a fire. It's funny though, because it's like, look all over the internet, just type for gas station fire, they're everywhere. Probably happened 2 or 3 times a year up until the last couple centuries when they're like, maybe we should ground those a little differently. But yeah, so that's why. Some materials like to hold on to their electrons, and there's places for them to hold on to them. Some shed them very, very easily. The slide is taking electrons from your pants. Okay. If you are comfortable with this and you understand it, give me a thumbs up. If any part of this is unclear, wave your hand around. Off we go. Okay. So here's calcium. Calcium's got 2 outer electrons. There's one of these questions on the test. Calcium has 2 outer electrons, that one and that one, that are shielded by the inner electrons. Now, obviously it's not perfectly scaled because calcium has 20, and I don't think there's 20 here. 1, 2, yeah, there's 20. So pretend this is calcium. So you got 2 outer electrons. The first outer electron is going to be easy to remove. It only takes us about 600 units of energy. The second outer electron is going to be a little bit harder, about 1100 units of energy. The third one's going to be really hard because once you take away 2, that outer shell is gone. And now that ion is isoelectronic with the noble gases. Remember, it's very hard to take an electron from noble gases. So you can see small, a little bit bigger, massive. Where you see this jump tells you what the ion is. If it's small, medium, large, huge, then this is a +3 ion. If it's small, then huge, it's a +1 ion. If it's small, then medium, then huge, it's a +2 ion. When that big jump happens, you're trying to take an electron from an element that, or an ion that is isoelectronic with a noble gas. Think about that for a second. If you're clear and you get that general idea, give me a thumbs up. If any part of that is unclear, write your hand around. Moving on. Okay, electronegativity. So electronegativity has another property that's too similar to teach it by itself called electron affinity. I mentioned this at the middle of last week when we were talking about the noble gas, the halogens. So electron affinity is the tendency or ability to attract electrons. Electronegativity is the ability to remove them from a nearby atom. So they basically follow the exact same pattern. They're just different things. So atoms' ability to attract electrons is electron affinity. Atoms' ability to absolutely remove them is electronegativity. So as more protons are added to the shell, then the protons attract the electrons of other atoms. So back to our diagram here. Imagine there's another atom, right there. Just for simplicity, we're going to give it 1 electron. That 1 electron is going to be attracted to this nucleus. The bigger this nucleus is, the more this nucleus will attract that electron. Make sense so far? But the more shielding you have, the less it will be able to attract it. So when we're talking about electronegativity, we are primarily talking about the nucleus of one atom attracting the electron of another atom. So the more protons you have, the higher your electronegativity will be. But that atom's electron shells will shield the nucleus. Fluorine is the king of electronegativity, or the queen if you watched you haven't watched that video holding electrons? I think you did, yeah. Fluorine is the queen of electronegativity. She holds on to her electrons really strongly because she's got 9 protons and only 2 electrons that are shielding. Chlorine's got chlorine's got 17 protons, but he's shielded by 10 electrons. So in general, as you move across the periodic table, you are adding protons, but they are shielded by the exact same effect across the table. And then as you go down the periodic table, you're adding whole new shells of shielding. Hey, come on, there we go. So halogens they have very high electron affinity. It's relatively easy for them to complete their octet because of their high electronegativity. They have lots of protons They're not shielded all that well. They can pull electrons from nearby atoms to complete their octet. All right. Krypton and xenon, we usually say noble gases are almost unreactive. We can make krypton and xenon react, which is why they technically have an electronegativity, but we usually just leave them off the table. Okay. Questions? If you're with me so far, give me a thumbs up. If you're like, I got a question, that's a chance. Okay, those are all the trends. Now we're talking about ions. This is kind of interesting. An anion is what we call it when an atom becomes a negative ion. Literally, a negative ion. Anions are always larger than their neutral atom. Why is that?
So what was the question?
Why is it in an anion, which is a negative ion, which has gained an electron, an atom has gained an electron, forming an anion, which literally means a negative ion, why are anions always larger than their neutral atom?
Because they're negative.
They're adding a more negative, and what do the negatives do? They repel. So by adding another electron to the cloud, that cloud expands because the electrons are repelling each other. Huh? Can you see that? Does that logically make sense to you?
No.
So you have a cloud of electrons, and they're repelling each other. They're like, they're fighting, right? And then you add one more to the brawl. Now there's more repulsion, and they have to expand because of it. Are we cool?
So what does the anion have to do with that?
Because if you take if a neutral atom takes an electron, it becomes negative. So a neutral atom, same number of protons and electrons, takes an atom, becomes negative, so it forms an anion, a negative ion. Cool? If you're ready to talk about positive ions, give me a thumbs up. If you have any questions, wave your hand. What do you think happens when you remove electrons from the electron cloud? It's smaller. It shrinks. Yeah. So a cation is called a positive ion. I don't have a good mnemonic for that. Just there's a T in there. Looks like a positive. Like if you get rid of the a positive ion. So a cation, only idiots call it a cation. A cation is a positive ion, and when you remove an electron, two things can happen. One, the outer shell encounters less repulsion, which should make sense. It's the opposite of the previous concept. But sometimes you shave off the entire outer shell. Yeah, question? Yes. So sometimes you shave off the entire outer shell, and that makes it real small. So if calcium, remember calcium has two outer electrons? If you take one, it shrinks a little bit. You take away the second one, the whole shell just disappears. So it goes +1, +2, because you shaved off the entire fourth shell. See, the electron shell, you like the outer shell when all of its electrons are removed. If all the electrons are removed, boom, it's gone. The whole shell disappears. Okay. How we doing? Questions? We're good? Moving on. So here's a summary of the periodic trends. It's on Canvas. Enjoy it. I don't really care about this.
I think
Oh.
picture that.
It's on Canvas. Yeah, the whole thing's on Canvas. You can access it. It's like the first thing. It says periodic trends notes. Okay, just like in the last question or last test, there's a 2-point extra credit question at the end of the test. It will be this. The atomic radius of elements in the same period decreases across the period. That we know. However, nitrogen is 70 picometers, while oxygen is 73 picometers. Why is that? So-
Oxygen's bigger.
It is, but why? That's the whole why. So if you can explain to me on your test Friday from after next, that's a lot of time to. Okay. Well, anyway, if you can explain to me why it is that oxygen's slightly larger than nitrogen, you get 2 points on your unit test. Question.
Because it has a larger electron configuration.
I'm going to allow you to research it and then tell me on Friday. Okay, so you can use the remainder of 15 minutes to work on worksheet 2 and the matching skills test. And I will be over there if you have any questions. Yes. And I got. You still streaming? Oh yeah, yeah you are.